Exploring the intersection of voice first technology and the blockchain coding on Solidity. Today is level 5, ERC 721, and Crypto-Collectibles. I have a feeling this is going to be stuff like NFTs, non-fungible tokens. Woo, things are starting to heat up, and we're going to learn some more advanced stuff. We're going to talk about ERC 721 and the crypto-collectible assets. In other words, we're going to make it so you can trade your zombies with your friends. We've got 15 chapters here. The first one, tokens on Ethereum. Let's talk about tokens. If you've been in the Ethereum space for any amount of time, you've probably heard of people talking about tokens, specifically ERC20 tokens. A token on Ethereum is basically just a smart contract that follows some common rules. Namely, it implements a set of standard functions that all other token contracts share, such as transfer from and balance of. Transfer from an address to an address with whatever token is being transferred, and then the balance to get the balance of an Ethereum wallet address. Internally, the smart contract usually has a mapping of address to a UINT 256, balances that keeps track of how much balance each user has. So basically, a token is just a contract that keeps track of who owns how much of that token and some functions so those users can transfer their tokens to other addresses. Why does it matter? Since all ERC20 tokens share the same set of functions with the same names, they can all be interacted with in the same ways. This means if you build an application that is capable of interacting with one ERC20 token, it's also capable of interacting with any ERC20 token. That way, more tokens can easily be added to your app in the future without needing to be custom coded. You could simply plug in a new token contract address and boom, your app has another token it could use. One example of this would be an exchange. When an exchange adds a new ERC20 token, really it just needs to add another smart contract it talks to. Users can tell that contract to send tokens to the exchange's wallet address, and the exchange can tell the contract to send the tokens back out to users when they request a withdrawal. The exchange only needs to implement this transfer logic once, then when it wants to add a new ERC20 token, it's simply a matter of adding a new contract address to its database. Other token standards. ERC20 tokens are really cool for tokens that act like currencies, but they're not particularly useful for representing zombies in our zombie game. For one, zombies aren't divisible like currencies. I can send you 0.237 ETH, but transferring you 0.237 of a zombie doesn't really make sense. Secondly, all zombies are not created equal. Your level 2 zombie Steve is not equal to my level 732 zombie Haxfield Morris. Not even close, Steve. There's another token standard that's much better fit for crypto collectibles like CryptoZombies, and they are called ERC 721 tokens. ERC 721 tokens are not interchangeable since each one of them is assumed to be unique and not divisible. You can only trade them in whole units, and each one has to have a unique ID, so these are a perfect fit for making our zombies tradable. Note that using a standard like ERC 721 has the benefit we don't have to implement the auction or escrow logic within our contract that determines how players can trade or sell our zombies. If we conform to the spec, someone else could build an exchange platform for crypto tradable 721 assets, but our ERC 721 zombies would be usable on that platform. So there are clear benefits to using a token standard instead of rolling your own trading logic. Put it to the test. We're going to dive into the ERC 721 implementation in the next chapter, but first, let's set out our file structure for this lesson. We're going to store all the ERC 721 logic in a contract called zombie ownership. First, we'll declare our pragma version of the top of the file. Then we will import the zombie attack.sol. Then we will declare a new contract, zombie ownership, that inherits from zombie attack. Leave the body of the contract empty. Okay, so we want our pragma. So we'll start with our pragma. Then we want to import /zombie attack.sol. Then after that, we want a new contract called zombie ownership. And that should be it. Oh, I need to say is zombie attack. That way it inherits all of the functions and variables from zombie attack. If I can spell contract right. There we go. Chapter 2, ERC 721 Standard and Multiple Inheritance. Let's take a look at the ERC 721 Standard. We have the contract of ERC 721 with the transfer event, the approval, the balance of, owner of, transfer from, and approve. This is the list of methods we'll need to implement, which we'll be doing over the coming chapters into pieces. It looks like a lot, but don't get overwhelmed. We're here to walk you through it. Implementing a token contract. When implementing a token contract, the first thing we can do is copy the interface to its own Solidity file and import it. Import erc721.sol. Then we have our contract inherit from it, and we override each method with a function definition. But wait, zombie ownership is already inheriting zombie attack. How can it also inherit ERC721? Luckily in Solidity, your contract can inherit from multiple contracts. We just add a comma, and then the new Satoshi Nakamoto is Nick Szabo and Hal Finney. As you can see, when using multiple inheritance, you just separate the multiple contracts you're inheriting from with a comma. In this case, our contract is inheriting from both Nick Szabo and Hal Finney. Satoshi Nakamoto is a made-up character. It's a pseudonym, and some people have speculated that both Nick Szabo and Hal Finney are the actual humans behind Satoshi, the creator of Bitcoin. Let's give it a try. We've already created the erc721.sol with the above interface for you. Import it into, so here's our ERC721. Import it, then declare that zombie ownership inherits from zombie attack and ERC721. Okay. Then we will import dot slash, then we will declare zombie ownership inherits ERC721. Chapter 3, Balance of and Owner of. Great, let's dive into the ERC721 implementation. We've gone ahead and copied the empty shell of the functions you'll be implementing in this lesson. In this chapter, we're going to be implementing the first two methods, balance of and owner of. This function, balance of, simply takes an address and returns how many tokens that address owns. In our case, tokens are zombies. Do you remember where in our DApp we stored how many zombies the owner has? I do. We stored it in the zombie count of zombie factory, owner zombie count, owner of. The owner of function takes a token ID, in our case a zombie ID, and returns the address of the person who owns it. Again, this is very straightforward for us to implement since we already have a mapping in our DApp that stores this information. We can implement this function in one line, just a return statement. Remember, our uint256 is equivalent to uint. We've been using uint in our code up until now, but we're using uint256 here because we copied and pasted it from the spec. Putting it to the test. I'll leave it to you to figure out how to implement these two functions. Each function should simply be one line of code or return statement. Take a look at our code from previous lessons to see where we're storing this data. If you can't figure it out, hit the show me the answer button for some help. Implement balance of to return the number of zombies owner has. Implement owner of to return the address of whoever the zombie ID with the token. Let's start with balance of. So here we're just going to return zombie owner zombie count of an address, return owner zombie count of underscore owner, which is the address. And then we just want to return the owner of a token here. So here we will return zombie to owner, zombie to owner of a uint of the token. So we'll then say underscore token ID Should be that simple. Got it. Chapter 4, refactoring. Uh-oh, we've just introduced an error in our code that will make it not compile. Did you notice? In the previous chapter, we defined a function called ownerof, but if you recall from lesson 4, we also created a modifier with the same name, ownerof, in zombiefeeding.sol. If you tried compiling this code, the compiler would give you an error saying you have a modifier and a function with the same name. So, should we just change the name of the function in zombie ownership to something else? No, we can't do that. Remember that we're using the ERC721 token standard, which means other contracts will expect our contract to have functions with the exact names defined. That's what makes these standards useful. If another contract knows our contract is ERC721 compliant, it can simply talk to us without needing to know anything about our internal implementation decisions. So that means we'll have to refactor our code from lesson 4 to change the name of the modifier to something else. Putting it to the test. We're back to zombiefeeding.sol. We're going to change the name of the modifier from ownerof to only ownerof. Okay. Change the name of the modifier, scroll down to the function feed and multiply, which uses this modifier. We'll need to change the name here as well. We'll also use this modifier in other files, but we don't spend too much of this lesson refactoring. We've gone ahead and changed the modifier names in those files for you. Great. Let's do number 1. We'll refactor, and now we will change it in feed and multiply. And I guess it's been refactored everywhere else, so that should be it. ERC721 transfer logic. Great, we fixed the conflict. Now we're going to continue our ERC721 implementation by looking at transferring ownership from one person to another. Note that the ERC721 spec has 2 different ways to transfer ownership. One is transfer from and approve. And then there's also transfer from, which looks the same. So I guess one is just transferring from, and then one is both approve and transfer from. The first way is the token's owner of transfer from with his address as the from parameter, the address he wants to transfer to as the to parameter, and the token ID of the token he wants to transfer to. Second way is the token's owner first calls approve with the address he wants to transfer to and the token ID. The contract then stores who is approved to take the token, usually in a mapping. Then when the owner or the approved address calls transfer from, the contract checks if message.sender is the owner or is approved by the owner to take the token, and if so, transfers the token. Okay. Notice that both methods contain the same transfer logic. In one case, the sender of the token calls the transfer from function. In the other, the owner of the approved receiver of the token calls it. So it makes sense for us to abstract this logic into its own private function underscore transfer, which is then called by transfer from. Putting it to the test, let's define the logic for transfer. Define a function named transfer. It takes 3 arguments, address from, address to, and token ID. It should be a private function. We have 2 mappings that will change the ownership changes. Owner zombie count, which keeps track of how many zombies an owner has, and zombie to owner, which keeps track of who owns what. First thing our function should do is increment owner zombie count for the person receiving the zombie. Address to, use the plus plus. Next, we'll need to decrease the owner zombie count for the person sending the zombie. Address from, use the minus minus to decrement. Lastly, we'll want to change zombie to owner mapping for this token ID so it points to 2. I lied, this wasn't the last step. There's one more thing we should do. The ERC721 spec includes a transfer event. The last line of this function should fire transfer with the correct information. Check ERC721.sol to see what arguments it's expecting to be called and implement it here. All right, let's get started with number 1. Define a function named transfer. Function. Oh, all of our tabs are off. Function underscore transfer. 3 arguments, an address of underscore from, an address of underscore to, and a uint 256 called underscore token ID. It should be a private function, so it can only be called within this smart contract. We have 2 mappings that will change when ownership changes, owner zombie count and zombie owner count. The first thing we should do is increment owner zombie count. Okay. Owner zombie count will pass in the address. So here we will owner zombie count, pass in the person receiving the zombie, so underscore 2, and then we want to say plus plus. Then we want to say owner zombie count of from minus minus. Lastly, we want to change zombie to owner mapping of this token. So now we say zombie to owner of underscore token ID equals underscore 2. I lied, that wasn't the last step. One more thing we should do, it specifies a transfer event. Let's add that transfer event transfer. So now we will emit transfer with from, to, and token ID. So we will pass in underscore from, underscore to, underscore token ID. Should be good. Chapter 6, ERC 721 transfer continued. Great, that was the difficult part. Now, implementing the external transfer from function will be easy since our transfer function already does almost all the heavy lifting. Putting it to the test. First, we want to make sure only the owner or the approved address of token zombie can transfer. Let's define a mapping called zombie approvals. It should map a uint to an address. This way, when someone that is not the owner calls transfer from with a token ID, we can use this mapping to quickly look up if he is approved to take that token. Next, let's add a require statement to transfer from. It should make sure that only the owner or the approved address of a token or zombie can transfer it. Lastly, don't forget to call transfer. Note, checking that only the owner of or the approved address of a zombie token can transfer it means at least one of these conditions must be true. Zombie owner for zombie token ID is equal to the message sender, or zombie approvals for the token ID is equal to the message sender. Don't worry about filling in data in the zombie approvals mapping. We'll do that in the next chapter. Let's start with number 1. Let's define a mapping called zombie approvals. Mapping, come on y'all. Let's keep all these tabs in line. Mapping, I think it's looking like this, mapping of uint to address, and then it'll be called zombie approvals. I think that's right. Next, let's add a require statement to transfer from. It should make sure that only the owner or the approved address of a zombie token can transfer it. Transfer from, add the require statement here, require. So we're going to require zombie approvals of underscore token ID equals underscore 2. How do we do an or? Is it same as JavaScript, just an or? Or we want to then check if zombie to owner of underscore token ID double equals, oh wait, not to, underscore message dot sender. Message dot sender. And then down here we will call underscore transfer with underscore from underscore to underscore token ID. Didn't do it right. Okay. I wonder how to do an or in Solidity. Or in Solidity. Logical or. How do you use the or? Should just be or. Okay. Zombie to owner of token ID equal to message.sender, which we're checking, or zombie approvals for token ID equals message.sender. We're comparing addresses here, so we might need to do a KeySack 256. Let's make this a hash. And then we'll do the KeySack 256 for message.sender. Okay. Oh, maybe it's because I'm missing a semicolon. Okay, let me undo this and just remove this and just add the semicolon. That wasn't it. Require that zombie approvals for token ID is equal to that. And you didn't like my KeySack 256, did you? What don't you like? No, 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 no. Okay, let me see what the answer is. A uint, zombie approvals, that's what I did. I think. I've lost it now. Require zombie to owner token is message.sender. It looks like I did it right, so I'm honestly not sure what was wrong there. We're just going to keep moving. Now the approve function. Let's implement approve. Remember with approve, the transfer happens in 2 steps. You, the owner, call approve and give it to the approved address of the new owner and the token ID you want him to take. The new owner calls transfer from with the token ID. Next, the contract checks to make sure the new owner has already been approved, and then the transfers happen. Because this happens in 2 function calls, we need to use the zombie approvals data structure to store who's been approved for what in between function calls. Putting it to the test. In the approve function, we want to make sure only the owner of the token can give someone approval to it, take it. So we need to add the only owner of modifier to approve. For the body of the function, set zombie approvals for token ID equal to approved address. So we will add into the approve function, we're going to add the only owner of from zombie factory, zombie feeding, and then we pass in a zombie ID, which is underscore token ID. And now in the body, set zombie approvals uint address. So we pass in the uint of token ID equals underscore approved. Chapter 8 ERC 721 approve. Great, we're almost done. There's one more thing we need to do. There's an approval event in the ERC 721 spec, so we should fire this event at the end of the approve function, putting it to the test. Let's fire the approval event, take a look at ERC 721 file for the arguments, and make sure message.sender as owner. Approval event, we'll use owner, approved, and token ID. Emit approval needs owner, approved, token ID. So the owner message.sender interesting. Then we want to pass in an approved and a token ID underscore approved. I get it. Okay. Message sender is the owner of the token originally. Approved is the person that's getting approved, and then the token ID is the token being transferred. I was confused and thrown through a loop as to why we were using message.sender, but that makes sense now. Chapter 9, Preventing Overflows. Congrats, that completes our ERC 721 and ERC 721X implementation. That wasn't so tough, was it? A lot of this Ethereum stuff sounds really complicated when you hear people talking about it. So the best way to understand it is to actually go through an implementation of it yourself. Keep in mind that this is only a minimal implementation. There are extra features we may want to add to our implementation, such as some extra checks to make sure the user doesn't actually transfer their zombies to address 0, which is called burning a token. Basically, it's sent to an address that no one has private key of, essentially making it unrecoverable. Or to put some basic auction logic in the dApp itself. Can you think of some ways we would implement that? But we wanted to keep this lesson manageable, so we went with the most basic implementation. If you want to see an example of a more in-depth implementation, you can take a look at the OpenZeppelin ERC 721 contract after this tutorial. Contract security enhancements, overflows, and underflows. We're going to look at one major security feature you should be aware of when writing smart contracts, preventing overflows and underflows. What's an overflow? Let's say we have a uint8, which can only have 8 bits. That means the largest number we can store is binary 1111, or in decimal 255. Let's take a look at the following code. What is number equal to at the end? 255, number plus plus, it's equal to 256, but it'll overflow. So number is counterintuitively now equal to 0, even though we increased it. If you add 1 to binary 11, it resets back to 0000, like a clock going from 2359 to 0000. An underflow is similar, where you subtract 1 from a uint8 that equals 0. It will now equal 255 because uints are unsigned, aka the u, and then int is integers, unsigned, and cannot be negative. Well, we're not using uint8 here, and it seems unlikely that uint256 will overflow when incrementing by 1 each time. It's a really big number. It's still good to put protections in our contract so that our dApp never has unexpected behavior in the future. Using SafeMath. To prevent this, OpenZeppelin has created a library called SafeMath that prevents these issues by default. But before we get into that, what's a library? A library is a special type of contract in Solidity. One of the things it is useful for is to attach functions to native data types. Functions to native data types. For example, with the SafeMath library, we'll use the syntax using SafeMath for uint256. The SafeMath library has 4 functions: add, subtract, multiply, and divide, and now we can access these functions from uint256 as follows. Using SafeMath for uint256, we set it as a value, then we add and multiply. We'll look at what these functions do in the next chapter, but for now, let's just add the SafeMath library to our contract. We've already included OpenZeppelin SafeMath library for you in safemath.sol. You can take a quick peek at the code now if you want, but we'll be looking to it at depth in the next chapter. First, let's tell our contract to use SafeMath. We'll do this in Zombie Factory, our very base contract. That way we can use it in any of the subcontracts that inherit from this one. Import safemath.sol into zombiefactory.sol. add the declaration using SafeMath for uint 256. Import dot slash, then we will declare SafeMath. That's it. Chapter 10, SafeMath Part 2. Let's take a look at the code behind SafeMath. We've got a library, a multiply function, a divide function, subtract function, an add function. First, we have the library keyword. Libraries are similar to contracts, but with a few differences for our purposes. Libraries allow us to use the using keyword, which automatically tacks on all of the library's methods to another data type. Using SafeMath for uints, we can use these methods on any uint. Uint test equals 2, test.multiply 3, now it equals 6, test.add 5, now equals 11. Note that the multiply and add functions each require 2 arguments, but when we declare using SafeMath for uint, the uint we call the function on is automatically passed in as the first argument. Let's look at the code behind add to see what SafeMath does. We take C, which equals A plus B, then we assert that C is greater than or equal to A, and then return C. So if for some reason C is an overflow, this assertion then fails, but I don't know what we would return then. Might just exit and throw it. Basically, add just adds 2 uints like plus, but it also contains an assert statement to make sure the sum is greater than A, thus protects us from overflows. Assert is similar to require, where it throws an error if false. The difference between assert and require is that require will refund the user the rest of their gas when a function fails, whereas assert will not. So most of the time you want to use require in your code. Assert is typically used when something has gone horribly wrong with the code, like a uint overflow. So simply put, SafeMath's add, subtract, multiply, and divide are functions that do the 4 basic math properties, but throw an error if an overflow or underflow occurs. Using SafeMath in our code. To prevent overflows and underflows, we can look for places in our code where we use the plus, minus, multiply, or divide and replace them with add, subtract, multiply, divide. So instead of doing plus plus, we would add 1. Putting it to the test. We have 2 places in zombie ownership where we used math operations. Let's swap them out with SafeMath. So we've got a plus plus. Let's do dot add 1, and then the minus minus dot sub 1. Why didn't you work? Why didn't you work? We pass the uint in, and owner zombie count should be mapped owner zombie count to a uint. Maybe I need to cast 1 as a uint? Not sure. We can't just say the add directly on it. We have to do this. I'm not sure why we have to do it this way, but we do. So we could just use the plus plus, but we can't just directly use the add for some reason. Oh, I guess we do have to set it. That would make sense. Chapter 11, Safe Math Part 3. Great, now our ERC 721 implementation is safe from overflow and underflow. Going back through the code we wrote in previous lesson, there's a few other places in our code that could be vulnerable to overflows and underflows. In zombie attack, we have win count, level, and loss count. We should prevent overflows here as well just to be safe. It's a good idea in general to use safe math instead of the basic math operations. Maybe in a future version of Solidity, these will be implemented by default, but for now we have to take extra security precautions in our code. However, we have a slight problem. Win count and loss count are uint 16s and level is a uint 32. So if we use SafeMath's add method with these arguments, it won't actually protect us from overflow since it will convert these types to uint 256. Add blah blah blah. If we call add on a uint 8, it gets converted to a uint 256, so then it won't overflow at 2 to the 8 since 256 is valid uint 256. So this means we're going to need to implement 2 more libraries to prevent overflow and underflow. We can call them SafeMath 16 and SafeMath 32. The code will be the exact same except all instances will be replaced with 32 or 16. We've gone ahead and implemented that code for you. Take a look at safemath.sol to see them. SafeMath 32, then we have SafeMath 16. Now we need to implement that in Zombie Factory. So assignment, declare that we're using SafeMath 32 for uint. This is going to be in Zombie Factory. So we will be saying, I think we can just delete this. Yeah, and we can do the same thing here. That's one more line of, there's one more line of code where we should use the SafeMath method. We've left a comment for you. Chose not to prevent the year 2038 problem, so don't need to worry about overflows. Our app is screwed in 2038 anyways. Let's use SafeMath's add here. Got it. Chapter 12, Safe Math Part 4. Great, now we can implement Safe Math on all the types of uints we used in our DApp. Let's fix all those potential issues in zombie attack. There was also one zombies zombie ID.level++ that needs to be fixed in zombie helper, but we've taken care of that so you don't have an extra chapter to do so. Go ahead and implement the safe math methods on all the plus plus increments in zombie attack. We've left comments in the code to make them easy to find. Zombie feeding. Zombie feeding is zombie factory. Zombie factory is ownable. Are we ever importing safe math though? Plus plus. Got that one. And another 2. Just code refactors. Okay, check the answer. Got it. Chapter 13, comments. The Solidity code for our zombie game is finally finished. In the next lessons, we'll look at how to deploy the code to Ethereum and how to interact with it with Web3.js. But one thing before we let you go on lesson 5, let's talk about commenting your code. Syntax for comments. Commenting in Solidity is just like JavaScript. You've already seen some examples. Single line codes, you just add a double / anywhere, it's easy. But I hear you, sometimes a single line is not enough. Multi-line comments, this looks exactly the same as JavaScript. Standard in Solidity is to use a format called natspec. Which looks like this: title, author, notice param XYZ. Title and author are straightforward. Notice explains to the user what the contract does. Dev is for explaining extra details to developers. Param is for describing what each parameter and return value are in the function. Note that you don't always have to use all these tags for every function. All tags are optional, but at the very least, leave a dev note explaining what each function does. Put it to the test. If you haven't noticed, the CryptoZombies answer checker ignores comments when it checks your answers. So we can't actually check your natspec code for this chapter. However, by now you're a Solidity whiz, so we're just going to assume you've got this. Give it a try anyway and add some natspec tags to zombie ownership. So natspec, we just use a double / triple / and you want a title, author, and dev. Triple / at title, zombie ownership, at author, at Voice First AI, and then at dev. This contract is for ownership of zombie tokens, of zombies. Oh, they already gave me values. Got it. Wrapping it up, that concludes lesson 5. As a reward, we've transferred ownership of your very own level 10 Haxfield Morris. Oh my god, the legendary Haxfield Morris zombie. Now you have 4 zombies in your army. Before you move on, you have the option of renaming any of them if you'd like. Click on the name, though I don't know why you'd ever want to rename Haxfield Morris. Clearly the best name ever. I don't know who Haxfield Morris is. Curious to look it up real quick. Don't know. In this lesson, we learned about tokens, libraries, how to prevent overflows and underflows, commenting your code. This lesson concludes our game's Solidity code. For now, we may even add more lessons in the future. In the next 2 lessons, we're going to look at how to deploy your contracts and interact with them using Web3.js so you can build a front end for your dApp. Go ahead and rename any of your zombies if you'd like, then proceed to the next chapter to complete the lesson. We did it. Thank you all for joining. If you've got any questions, message us on any social media site at Voice First AI. Otherwise, have a great rest of your day.